All right, this is AP Calculus Worksheet 8-4. This is the key. I don't know why I'm doing all lowercase. Let's do capital key. I have some mosquitoes. The rate is modeled by that equation. There's our start condition, 1,000, and there's our start time. Time is equal to 0. Write an expression for capital M of t at any time t, not just 3. So capital M of t is going to equal the start plus change equals n, so 1,000 plus the change from the start time 0 to the end time, well, we don't know, so I'll just say end time of t of our capital R of t in this case. So capital R of t dt. Okay, easy enough. Find the maximum number of mosquitoes and then show the analysis. So whenever you see maximum or minimum, you're going to be making a table. Let's make our table. And there's a fancy, oh, that's not quite straight, fancy table. We're going to have times t. We're going to do start plus change. That's going to equal to our end value. I guess this does not need to be so long. Let's go ahead and graph this thing. So I've already graphed this thing before. My y equals is set equal to the correct function. My window is between 0 and 31. If I come over here to my graph, that's what our graph looks like. I should probably copy and paste this guy in here so we have it for the key. And again, we're looking for the maximum value. So the maximum value is where I'm going to have a positive to a minimum height, or positive to a negative height. So I have a positive to a negative height right there. So this is going to be a maximum, possibly, but you always want to check start and your end. In terms of the analysis for this, it doesn't make sense for your start condition right here to be a maximum because it's followed by positive area. So that's obviously not going to be the answer. It could be this. Then I have this negative area down here, so it can't be this value right here. In fact, that goes from a negative height to a positive height up here. So that's a minimum value. But then all of a sudden I have some positive area happening up here. So I could have a maximum right there. If I'm being very, very astute, I'll notice that the area down here is much bigger than the area up here, which means the maximum probably will happen at this point, whatever that point is. Let's come back and enter our times. We always need to check your start. You always need to check your end. In fact, you don't really need to check your start in this case. I'm pretty sure you could exclude it. You definitely want to check your end, though, just to calculate it. My end value is 31, and I want to find whatever this value is. So to find this t value right, maybe my line could be a little bit straighter. This t value right here, I need to calculate that. So I have to do second trace to calculate the 0. So I hit 2. I'm going to guess there it's about, I don't know, 9-ish. So I'm going to guess between 5 and 15, and I'm going to guess 9. Let's see how close I was. This is going to be 7. 7.854. So I'll write down this was 7.854, and that's the other t value that I need, 7.854. You could find the other value that's over here. I think that's going to be like 23.562, but we don't need that value. So my start condition, I told us, we start with 1,000 mosquitoes, so we start with 1,000 and 1,000. And I'm going to do my change. My change is always going to be the integral between 0 and whatever this t value is. Why did I start at 0? Because that is the initial, my initial t value up here. I thought I covered it for a sec, but I didn't. So t is equal to 0, that's why those two match up. And then this upper bound is going to be whatever this t value is, so plus the integral from our start time to 7.854. 7.854 plus the integral from 0 to 31. And all of this is taking the integral of capital M, capital M, capital M. Again, just generalizing it would be, wait, not M. That's embarrassing. Capital R. Capital R and capital R. This function up here. And I could say R of t dt to be formal, but no, I'm going to go fast. So that's obviously 0 to 0, so that's just 1,000. Whenever it's the same bounds, it's gone. And I do need to calculate this thing. I can do it graphically. I could do second trace to do the integral here. A slightly faster way is doing math 9 vars right. Enter y1 with respect to x from 0 to 7.854. And then whatever this spits out, I'm going to add 1,000. I think this is going to be like 39 or something. So this is going to be 1,000 and 39. I'm rounding to the nearest whole mosquito too, because it says to the nearest whole number. So that's why I'm going to round to 1,039. This would show me my work if it's correct or not. Go, calculator, go. There it is, 39.357, and you're just rounding to the nearest whole number, so 1039. And then finally I do this integral down here, and it's going to be the same thing you do. You can do second enter to get back to the previous line, and you can hover over this 7 point blah blah blah, hit delete, 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 and I can just type in 31. And this number is going to round to something like negative 36 or something like that. So it's going to be a negative amount because this negative area was bigger than the positive area. So the answer down here is going to be 964 once that actually pops up. Again, we're always adding that to our initial condition, 1,000. So where does our maximum happen? Our maximum happens with 1,039 mosquitoes at time is equal to 7.854 days. So that is our max. And I can type that out to just to get in the habit of saying that. Let's come down here to 12 size font. Max is 1,039 mosquitoes at t is equal to 7.854. You should get in the habit of writing down your conclusion with the number the amount and the time. Let's come back and check our calculator. It was negative 36, running to the nearest whole number, which is how we got 964. You can always just say plus 1,000. Let me use my stylus so it's faster. Plus 1,000, and you'll see, oh yeah, 964, running to the nearest whole number. All right, so that was number one. We're now on to number two. And I need to enter these into my calculators. Let me do that off screen really quickly. All right, so I have all the equations in. I did y1 minus y2, this entering minus the leaving, and that y3 is graphed here. And let's go ahead and do part A now. By the way, the window is from 9 to 23 as well. Write an expression for P, so capital P of t. What is this thing? It's the total number of people in the amusement park at time t, so this is going to be the integral, sorry, what is the start amount? There is no start amount. Okay, so it's just going to be, oh, what happened there? Will they go away? Okay, so it's the integral from 9 to t, because our start boundary is 9 now. And, oh yeah, so we do have a start condition. Our start condition is 0. There are no people. 9 to t, and that's going to be the entering, the capital E of t, minus capital L of t. All of this thing times dt. Yeah, I'll need that for this next part. B, at what time does the model predict the number of the park is a minimum? So minimum, you want to be thinking of a negative height to a positive height. So analyzing this graph, and I, again, will screenshot this to put it in our notes. Sure, we'll put it like over here. Our minimum value is going to go from a negative to a positive, and it never does. It only goes from a positive to a positive height to a negative height. So we don't really have any critical values to check. I mean, you could put in that one. It's not going to work, though. I'm really only going to want to check my start and my end value. In fact, I have a feeling, I feel like this area is bigger than this area. I might be wrong, though. If this area is bigger, then that means that the minimum happens right here. But it's either the beginning or the end is my guess. So let's go ahead and make our table again. Let's make our quick table. Chunk, and chunk. We need times t. We're going to do start plus change. That's going to equal our end. So our start time is 9, our end time is 23, and I'm not going to check the critical value. I don't even need to find that value. So our start is 0, 0. Our change is the integral from 9 to 9 of e minus L, so don't even worry about it. This is going to be the integral, so that's 0, right? And this is going to be the integral between 9 and 23 of capital E minus capital L. So let's figure out what that is. So if I get out of this, again, my y3 function is the one that's subtracting E minus L. So if I go math 9, my var is right, enter 3, my y3 function with respect to x from 9 to 23, I'll get a number. And I think that number is 1. If we round to the nearest whole person, let's see what it is. If you actually found, 1.013, but it's the total number of people, right? So this is just one person. I'm rounding here to the whole number. And if I actually did calculate whatever that was, what is it going to be, like 15.795 or something like that, you'll find that if you actually plug in that value, it's going to be like 3,951 people. We definitely did not need to do that. So the correct answer here is we'll circle it. The minimum is right there and at that time. And typing it out in words, the minimum happens at t is equal to 9 days? 9 hours. 9 hours with 0 people. Perfect. All right, on to number 3. Okay, we have a graphical one now. This is number 3. 700 people in line. I realized that my last video I kind of made a mistake because there are people entering the line. So this is entering, this is our positive rate, which we don't know what's happening, but we do know that this is, oh, we do know what it is. There it is, it's R of t right there. And there are 700 people, so that's our start condition. And while there's a line, people move onto the ride, which means out of the line at a rate of 800. So that's our negative rate right there for the 800. At what time t is the ride the longest? So it's looking for a maximum value. So that's going to be a little bit tricky. How are we going to do this one? Well, we know that this is going to be the positive rate, and the negative rate is a constant negative 800. So I can kind of graph the negative rate on here, right? So if I were to graph this line right here, that's what 800 looks like. So whenever I have positive area up here, that means more people are getting on the line, and then all of a sudden right here, now people are starting to get off the ride faster than they're getting on. Again, this line represents your negative rate, right? So this is, if I'm at this point, that means I'm getting 800 people off and I'm getting 400 people on the ride. So in this area over here, that means that's our negative area. Hopefully I've explained that well enough. Let me look at my notes from last time. And I did it totally different last time, which is kind of interesting. Again, you still do need to make a table, so I'll go ahead and get that set up. Table. Those are the t values, start plus change, and then the right area is going to be our end value. So t, we need start plus change, and that's going to equal to our end value. So we obviously want to have the start and end amount. So does it say how long this thing lasts? I guess until 8, right? Closes 8 hours later, so between 0 and 8. But what critical values do we need? And it's only this one, wherever these two graphs intersect each other, and that's at time is equal to 3. So only those values. What is our start amount? Start amount is 700, I said over there. 700, 700, and 700. And our change is going to be an integral between our start time, which is 0, to this time over here, 0, integral from 0 to 3, integral from 0 to 8. I'm adding each of these to the start condition of, and then what I'm really doing is I'm doing positive r of t. I guess I'll just do lowercase r minus whatever this 800 is. So r minus 800, lowercase r minus 800, and again, lowercase r minus 800. So the change here is going to be a little bit interesting. I'm going to have to find some area here. So let me get rid of those bars so I can actually write some stuff. All right, so if I'm finding between 0 and 0, that's obviously gone. That's just 700, nice and easy. Okay, 0 and 3 though, so I have to find all that area that I just shaded. If I zoom in here, it's not the highest quality. I can break this up into 3 different shapes. I have a rectangle down here, which is 2 by 200. This height here is 200, which is 400. 400. And then each of these triangles is exactly half of that. It's as if I cut that rectangle in half, right? So half of that, ooh, what happened there? Scroll down and up again, will that fix it? That means that must be 200, 200, and this also right here must be 200. Adding all those together, I get 800. So that's positive area because it's above this line, right? Positive area, so zoomed up. So it's going to be 700 plus 800, which is 1,500. And then obviously we don't need to really check this other stuff, but I need to find the area underneath this line, which is really weird to think about. You normally think of, okay, I find this area right here first, and then I I'll find this area right here a second, and then I'll subtract one from the other, which is really just trying to find this area right here. If I find that area right there, that is the negative amount, because I have the positive rate, which is this graph of r, minus this blue line, which is essentially saying, hey, there's your new x-axis. If you're above, that's positive. If you're below, that's negative. So let's find all of these areas. Well, we know that that one is going to be 200 right there. I have a rectangle right here, which is 4 by 400. 400 is the height, so that's 1600. 1600. By the way, all these are negative amounts, I should say. And this triangle right here is 2 by 400, which is 400. Because 2 times 400 is 800, but then divide by 2 is 400. So I have a negative 400 there. Adding those all together, I get negative 2,000 there, negative 2,200. So I come back down here and I say, oh, wait, that does not make sense. How do you have negative? Oh, because I have to add from 0 to 8. I was doing from 3 to 8. So that negative area is negative 2,200. I'll write it down. But then I have to add all the positive rate. The positive rate was 1,500, right? So it's 1,500 minus 2,200, which is negative 700. And 700 minus 700 is 0. And it told us that in the problem that the park closes 8 hours later, so there shouldn't be any people in the park theoretically in the real problem. So that actually works out nicely. All right, this all boils down to a final answer of saying what is the ride that, or when is the line the longest? What is the biggest value? There it is. It's at time is equal to 3. So let's come down here and type in our final answer. Oh, what happened to all of our? It'll fix itself later. I'm thinking there it is. So the line is longest at t is equal to 3 hours with 1,500 people. Cool. Oh, wow, that's it. That was the last question, number 3. And that concludes worksheet 8-4.